Let's solve another thermodynamics problem, this one involving a polytropic process utilizing propane in a piston cylinder. A piston cylinder assembly contains propane, initially at 27 C, 1 bar, and a volume of 0.2 cubic meters. The propane undergoes a process to a final pressure of 4 bar, during which the pressure-volume relationship is PV to the 1.1 power equal constant. For the propane, evaluate the work and heat transfer, each in kilojoules. Kinetic and potential energy effects can be ignored. Let's lay out our storyboard for this problem. We'll start with a schematic of the system. We have a piston cylinder assembly, and my boundary line, the system boundary line defines that the propane is our system. Only the propane molecules constitute our system. Let's look at the given data. This is a single process. Begins at state 1, where its temperature is 27 degrees C. The pressure is 1 bar, and the volume is 0.2 cubic meters. After the polytropic process takes the propane to state 2, we know the pressure is 4 bar. And we know the process that took us from state 1 to state 2 is PV to the 1.1 power is equal a constant. Let's draw this process on a PV diagram. State 1 is located here at a pressure of 1 bar and a volume of 0.2 cubic meters. A polytropic process with an exponent value n of 1.1 will always look like a concave curve. Okay, so I'm drawing this, taking us up to state 2, and it ends when this process reaches a pressure of 4 bar. The volume at state 2, we'll just call V2 because it is, as of this point, unknown. We're going to model this as a closed system, of course, and where kinetic and potential energy effects are negligible and assumed to be 0. And the process is a polytropic process with n equals 1.1. And we need to find the work done by this process and the amount of energy transferred into the system during the process. So we start out by finding V2, and we'll use the polytropic expression to do that. We know that PV to the n power is a constant, and in this particular case, with n equal 1.1, we can write that P1V1 to the 1.1 power equals P2V2 to the 1.1 power. And our unknown is V2, so let's separate that. And we get V2 to the 1.1 power is the quantity P1 over P2 times V1 to the 1.1 power. Well, we can solve for V2 by raising both sides of this equation to the 1 over 1.1 power. So V2 is equal to the quantity P1 over P2 raised to the 1 over 1.1 power, all times V1. Well, we know P1 is 1 bar and we know P2 is 4 bar. We'll raise that quotient to the 1 over 1.1 power, multiply by V1, which is 0.2 cubic meters, and we get a value for V2 is equal to 0.0567 cubic meters. Now we want to find the work done during this process. And this is a polytropic process with n not equal to 1. And in a previous lesson, we solved the integral of PdV for this particular situation. And we came up with the algebraic expression that the work is equal to P2V2 minus P1V1 all over 1 minus n. Well, we have all of these values. P2 is 4 bar. V2 is 0.0567 cubic meters. P1 is 1 bar and V1 is 0.2 cubic meters. N has a value of 1.1. This will yield units of bar cubic meters, and 1 bar cubic meter is equivalent to 100 kilojoules. So the work done by the process is, or I should say done by the system during this process, is a minus 26.8 kilojoules. And the negative indicates that work had to be put into the system in order for the process to take place, which makes sense because the initial pressure was 1 bar, the final pressure was 4 bar. So we're compressing the gas, and therefore work has to be added to the system in order for that compression to take place. Now we want to find the U values. So we can go to the, for state 1, we're going to go to the saturation table at 1 bar. And we find that the saturation pressure is minus 42 degrees C. But we have a temperature of 27 degrees C, which is greater than the saturation temperature. So we know that state 1 is superheated vapor. So let's go to the superheat table. And state 1 is defined by pressure and temperature. It's 1 bar at 27 degrees C. And so at the 1 bar subtable in the superheat table, I'm looking for 27 degrees. Well, I can't find 27 degrees. I find 20 and I find 30. And so I can get the values for V and U at each of these temperatures. To find them at 27 degrees, I'm going to have to interpolate. So the way I interpolate, I like to use this F value, which is actually an interpolation factor, or it's a fractional factor. Essentially, it's how far I am between the first row and the second row in this table. And since I'm at a temperature of 27 degrees, F is 27 minus the value in the first row over the value in the second row minus the value in the first row. So I find that the interpolation factor is 0.7, which makes sense. 27 degrees is 70% of the distance between 20 and 30. So V1 is the value of a specific volume at 20 degrees plus my interpolation factor times the value of a specific volume at 30 degrees minus the specific volume at 20 degrees. I can take all those values out of this table, and I get V1 is 0.5571 cubic meters per kilogram. We do exactly the same thing for interpolating the internal energy. It's the value in the first row at 20 degrees plus 0.7 times the value in the second row minus the value in the first row. And I get U1 is 473.73 kilojoules per kilogram. Now we're going to need the mass of the system. And we can find that at state 1 because the mass is just the volume divided by the specific volume. And we have both those values for state 1. The volume at state 1 was 0.2 cubic meters, and we just got a value out of the table for specific volume, which is 0.5571 cubic meters per kilogram. So we have a mass in the system of 0.359 kilograms. Let's calculate properties for state 2. Well, we can calculate the specific volume at state 2 directly. It's just the volume divided by the mass. And we know the volume at state 2. We found it through the polytropic process equation. It was 0.0567 cubic meters. And we just calculated the mass of 0.3591 kilograms. So we know the specific volume at state 2 is 0.1579 cubic meters per kilogram. So now we have two independent properties defining state 2. We know that state 2 has a pressure of 4 bar and a specific volume of 0.1579 cubic meters per kilogram. And I found the following information in the 4 bar superheat table. I found that this value of a specific volume that I'm looking for is between the specific volume given at 70 degrees and 80 degrees. And again, this is in the 4 bar superheat table. So I know that the properties of, I know my internal energy is somewhere between these two values given in the table. So again, we're going to have to perform a table interpolation. So we can say that the internal energy at state 2 is the internal energy given at 70 degrees plus some fractional value times the internal energy at 80 degrees minus the internal energy at 70 degrees, where this fractional value is based on my knowledge of the specific volumes, how far between these two rows is this state? Well, we calculate F as V2 minus V70 over V80 minus V70. I get a fractional value of 0.5686, which means we're just a little over halfway between the values in row 1 and the values in row 2. So let's calculate the internal energy at state 2. It's the initial value, the value in the first row, 538.1, plus this fractional value we computed, times the U value in the second row minus the U value in the first row. And so we have an internal energy at state 2 of 548.11 kilojoules per kilogram. Now we can use the first law, write an energy balance, to find the heat transfer during this process. We know that when kinetic and potential energy terms are eliminated, that our energy balance reduces to delta U is Q minus W. Okay. Well, Q for this process 1,2 can be written as the change in internal energy, which is the mass times the change in internal energy, plus the work done during the process. We have all of these terms. We know the mass, we have the internal energy at state 2, or I should say the specific internal energy at state 2, minus the specific internal energy at state 1, plus the work term, which is negative. And I calculate that the heat transfer during this process is minus 0.1 kilojoules, which is very nearly zero. Not quite zero, but very close to zero. Let's explore the meaning of that. So if Q is 0, that is called an adiabatic process. So an adiabatic process has no heat transfer and Q is 0. In this particular problem, we were very close to being an adiabatic process. Why is that? Well, let's look at our polytropic process. And for our polytropic process, we had a value of 1.1. Now, when the value of N in a polytropic process is equal to K, which I'll mention here momentarily, then that describes an adiabatic process. We went over this in a previous lesson. Well, what is K? Well, it's just the ratio of specific heat, C sub P over C sub V. And we haven't done specific heats yet. But let me just show you that the value of K for propane during this process is very nearly, it's 1.13. Well, we used the value of 1.1. Well, it's not quite the same, but it's very close. If we had used a value of N of 1.13, which is K, then we would have had an adiabatic process and Q would have been exactly 0. But because we used a value that was close and not 1.13, but 1.1, we came out with a very tiny bit of heat transfer. It was close to 0, but it's not completely adiabatic.